The fact that you can talk to people who have had some impact on your career, kind of listening to how they think, how down to earth they are, is just, great.
Today we'll be talking about software validation, and now you can see the definition by ISO, but essentially it means making sure that the software does what it's supposed to do. And this is a fairly generic statement, so let's get more specific. One aspect of software validation is security, which means how resistant the software is to attacks. There are many different kinds of attacks, like backdoor attacks, which is when an attacker tries to add malicious code into an existing project. There are also hardware-related attacks like Spectre and Meltdown, which uses a hardware side channel to leak data. Today we will not be focusing on these two. Instead, we will be focusing on accidental software vulnerabilities. So accidental, not intentional, and software, not hardware. Memory safety refers to the protection of software vulnerabilities that use memory access, like buffer overflow or dangling pointers. One way such a vulnerability can happen is with invalidation, which happens whenever an object gets modified or deallocated, causing a reference or a pointer to become invalid. Here we take a reference to the first element of the vector. Then we call pushback. The call to pushback can potentially cause the vector to reallocate, and if it does, then the reference will still keep pointing to the old buffer of the vector. Then when we think that we are printing the first element, instead we may print some other data that we don't want to. There are also out-of-bounds related vulnerabilities, which is whenever we are accessing memory outside the bounds of a buffer or a container. Here we have a potential out-of-bounds access, because if the index is outside of the valid range of the vector, then it can overwrite other piece of memory, like a function pointer or some permissions. There are also vulnerabilities that are not related to memory access or to memory safety. One of them is injection. And this happens whenever the program allows an attacker to pass malicious code to another system. Here is an example of an SQL injection. And this kind of vulnerabilities can also happen in languages which are considered memory safe. For example, the Java library log4j had one fairly recently, and also Rust standard library had a command injection vulnerability on Windows. There is also memory safety, which even though it uses the term safety, it is very different than memory safety, and it refers to the risk or harm that the program can cause. So think about unintentional damage to people, other living beings, the environment, or equipment. One recent example of it is the CrowdStrike incident, which, due to a faulty update, crashed roughly 8.5 million systems, affecting many businesses and industries all over the world. This one I talked about. There is also performance-related requirements. So many applications have performance requirements, and they can be different between applications. So real-time applications usually care about latency in the range of milliseconds. For high-frequency trading, the range is usually nanoseconds. Mobile applications may want to improve performance to reduce battery usage for their users, and cloud providers may want to improve it to reduce their electricity consumption. There are also many other kinds of validations, so here are just a few more examples. You may want to validate your business logic or how your software interacts with another device. Could be the GPU if it's on the same system, or with another device through the network. Error detection can happen statically, which happens without running the code, and it can potentially catch the issues early. It can also happen during the execution of the program. Both ways should be used together to detect as many issues as possible. Keep in mind that compile time validation is part of static validation because it happens without running the code. Now here we have a potential out-of-bound access. We can't statically know whether the index will be inside the bounds or outside the bounds of the vector, but we can statically know that there is a potential issue here. We can replace the access of the vector by using std_vector@, and this one uses bounds check. So if the index is outside of the bounds, it will throw an exception. Now, once again, we can't know if statically if the index will be in bounds, but we can statically know that there is a runtime check for it, and therefore knows that it will never access outside memory outside the range. We can also validate performance, and this can be done at runtime. So we can query the high-resolution clock at the beginning and end of the function, and then validate that we match the performance target. We can also detect performance issues statically. So if the must-be-fast function can slowly read a huge file, then it will not be fast. Now, in this example, it is pretty obvious to see. However, if the call to read a file happens to be inside of a branch in a nested function, then a human can miss it. So here is a typical software development pipeline. So we start with the design, which is when we think about the code. And ideally, we would like to detect all issues at this step and write flawless code on the first try. However, this is not realistic. So then we build the code, we test it, it gets to code review and merged in. At this point, it also affects at least part, if not the entire development team. After it, there are more tests, and then it gets rolled into production, at which point it also affects the users. Now, we want to detect the issue as early as possible, both to minimize the risks that the issue can cause, and also to reduce the iteration times. Just detecting the error is not enough, we also have to report it, and the error message should be as clear and informative as possible, and also point to the right location so that the error will be able to be fixed quickly. C++ has many dangerous features, and you can think of them like using knives. So we do need to use the knives when we are cooking. However, if by any chance we make a mistake, we may cut ourselves or blow off a whole leg. What we want to do is compile time validation, is we want to explain to the compiler how we are planning to use these knives in our program. And the compiler will look at it and either say, oh, these are some dangerous knives, but you're using them in a completely safe way, so go ahead. Or it will give us a compilation error that says these specific knives may cut something it's not supposed to. Now, in a recent talk, Herb Sutter used the mech suit analogy, so the mech suit gives you safety. However, if you need to get into the water, which is an analogy to having high performance or high control over the program, then you want to get outside of the mech suit, otherwise you will drown. So there is a choice between safety and flexibility. However, many C++ applications need high performance and control. So if we know that we are going to get into the water, we should be aiming to design a mech suit that can swim, so that we can have both safety and flexibility at the same time. Here is a typical runtime error reporting. So we try to detect an error, and if we manage to detect it, then we report it. We will start from the error detection part, because this won't change, unlike the various error detection mechanisms. Even if we detect the error at compile time, we can still report it at runtime. Keep in mind that these two steps are separate. But we still want to report it in compile time, so we can use static assert for it. One limitation of static assert is that the error message must be a string literal, so we can't take information from the error variable and put it inside the error message. But let's try to do it anyway. So this costume error struct will be the error message, and if we detect an error, then we report the error and pass the struct as a non-typed template parameter. Inside the report error function, we have a static assert that will always fail, because sizeof can never be 0. If we look at the generated error message, we can see the costume error as part of the template instantiation stack, but the error message itself says that it failed because 1 does not equal 0. And this is not the error message that we want. We can move the size of comparison into an inline context per variable, and then use this variable inside of the static assert. Now it fails with always false of an error, and it says that the error is our costume error, so we managed to print it. We can add data members into our error message struct, and their values will be printed as part of the error message. A fixed string is a wrapper around a fixed size array of characters, and because it has a Contextual constructor, we can use it to represent and pass around a compile time string. If we pass a fixed string into the report error function, then for Clang and GCC, it will print the string as part of the error message. However, for MSVC, it will print all the characters as ASCII numbers. In C++26, we get user-generated error messages in static assert, which allows us to pass an object that has a size and data methods. So we can use std_string to generate a detailed error message at compile time and report it. Now, we can use unit tests to detect individual components and test them. And in C++, many components and computation can run at compile time, and therefore can also be tested at compile time. This is the compile time unit test setup. So here we have static assert with an immediately invoked lambda, followed by comma true. Inside the lambda, we can have more static assert to test various components of our program. The benefit of this approach is that because it is inside of a static assert, it can be placed pretty much anywhere. It can be inside of a function, a class, or a namespace. And because all of the unit tests happen inside of the lambda, it will not pollute the outer scope. cplusplus is a set of compile time libraries that uses compile time unit test to validate its components. The test that you see here happens to be inside of the test setups that we saw in the previous slide. And if there is any change that will break one of these tests, it will be detected at compile time. Now, with unit tests, we are able to check that the API works correctly, but we want to also validate that the API is used correctly and detect whenever something breaks it. We will look at an enum as an example. So here we have an enum with two options, and we have a switch case over a value of this enum that does something different for each case. If we add a third option to the enum, we may forget to add it to add a case for it in the switch case. One option to solve this issue is by using the magic enum library, and it has a function that counts the amount of options that the enum have. So we can put a static assert before the switch statement that asserts it to be 2. And if a third option will be added, then the static assert will fail and point us to the location in the code that needs to be addressed. However, a better option is to use the enum switch function, which converts a runtime value of the enum into a compile time value one. And then we can handle each different case in a if context per branch. And in the else branch, put a static assert that will always fail. If more options added to the enum, then the static assert will fail until we will add if context per branch to handle all of them. There is a proposal to add reflection to C++26, and here are some of the details. So the reflection operators can take some compile time value, like a type, and returns the meta information about it. There are also meta functions that allow us to access more meta informations, like the members of a type or the name of it. And the splice operator is the opposite of the reflection operator. So it takes the meta information about a type or compile time value and replaces them with the actual type or the compile time value. We can implement enum switch with C++26 reflection with just a few lines of code. So here we have a function that takes a callback and the enum value, and we reflect all the options inside of the enum type and pass them to a lambda. Then we compare each option with the enum value, and if they match, we call the callback with the option. Let's borrow some principles from functional programming to use in our compile time validation. So in both functional programming and compile time programming, it is common to work with immutable data. One way to get around it is to always create new data structures with the desired changes. So think about copy on write. Function compositions allows us to compose new, more basic functions into more complex ones, and monads encapsulate a context that can pass through multiple operations. We will look soon at each of them in more detail. Let's start from the function composition. One way to compose functions is through the return type. So we call the first function and we pass the return value of the first function as the argument to the next one. Another way is with continuation, where each function takes a callback to the next function. So here f1 takes a callback to f2, which takes callback to the next continuation. There are a few benefits to the continuation approach. One of them is the internal iteration, because we can invoke the next function as many times as we want from the current function. It also prevents dangling references. So here we have a vector, and we invoke the next function with a std span of that vector. And this is completely valid. However, if it was a return statement instead, then we will have returned std span that refers to a local vector, which will be destroyed when we exit the function. Now, if we know when we're composing function, if we know the properties of the components, then we can use them to compute the properties of the new function. Let's look at an example. Assume we care about the performance characteristic of the function, whether it is memory safe or if it can terminate the program. Then we can create a compose function that takes the properties of the component and computes the new one. So the performance characteristic will be the worst of the two because it will be invoking both of them. It will be memory safe only if all the components are memory safe, and it can terminate the program if at least one of the components can terminate it. A value wrapper is a small utility that wraps around a compile time value, which it takes a non-type template parameter and allows us to pass it as a function argument. Our composable function will take the properties as a value wrapper, and it will also include a stateless lambda, and this will be the actual callable. Yes?
Could you slow down a little bit, please?
Oh, sorry. So the pipe operator, we will use it to compose the functions. First, it will compose the properties and pass them to the new composed function. And then it will also compose the callables with the continuation approach. So F1 will invoke F2, which will then invoke the next function. This is the same logic that we saw before. It looks slightly different because of C++ forwarding syntax. Okay, now we can create some composable functions. So here we can have one that is called unsafe index, and it accesses a vector with an index without doing a bounce check. And in the properties, we can mark it as not memory safe. We can have another version that use the bounce check access function of the vector and mark it as memory safe. Then we can create more components, and once we finish composing them into a function, we can static assert that it validates the requirements. In this case, we assert that it is memory safe, and therefore we know that all of the components are also memory safe. Now, std_expected can represent either a value or an error. We don't know which one it is until we check it. It's kind of like Schrodinger's cat. And if we try to access a value or an error that doesn't exist, it will throw an exception. It also has monadic operations, like the transform method, that will call the callback only if it contains a value. So outside of the scope of the callback, the type of the result is either some kind of error or value. And inside the callback, we have the value types that we can safely use. We can chain multiple transform operations and change the context type in between them. Let's see how we can use it at compile time. So a context variable is a wrapper around a reference of type t, where t must have an ID, which is a compile time identifier, and also an apply method, which takes an action and returns the next type it should be transformed into. Now, how can we change a type? How can we change the type of a reference? One way to do it is by reinterpret casting the reference into a reference and a new type, and then wrapping it again in a context variable, so using the copy on write mechanism. Then a context is a tuple of context variable, so essentially a tuple of references. And whenever an action is applied, we apply the actions to all the context variable, and once again wrap them in a context tuple. Now let's implement an optional that we can validate at compile time. So here we have the destroy action, which will be used to notify whenever the optional is destroyed. There is also a compile time state of whether it exists, and the optional class contains a std optional and two additional template parameters, the compile time ID and the state. Whenever a destroy action gets applied, we tell the context to change the type to mark the optional that it no longer exists. Whenever we call the reset function of the optional, then first we reset the std optional itself, and then we apply the destroy action to change the type of it. Finally, whenever we try to access the optional, we assert that we statically know that it currently exists. Let's also detect reference invalidation. So here we have a reference type that has two methods. One of them to get the reference, and it first asserts that it is valid. So the reference takes more template parameter. One of them is the identifier of the objects that it points to, and another is whether it's valid. Whenever an apply function gets detected that says that the object that the reference points to is destroyed, we change the type of the reference to mark it that it is no longer valid. Now we can compose multiple functions and change the context type in between them. So the first function creates an optional and creates a reference to the value of that optional. Then we add them both to the context and pass it to the next function. In the next function, we reset the optional, which will apply the destroy action, marking the optional as no longer exists and the reference is invalid. Now, in the function in the last scope, we will try to get the reference. However, in this scope, its type is invalid, so it will fail with a static assert. Now, there are some drawbacks to this approach. First one is that it is using functional programming, and whether to use functional programming or not should be a design decision, not a requirement for writing compile-time valid code. It also relies on compiler optimization, like inlining, tail call optimization, and removing all the references, which compilers are very good at doing for release builds, but not so much for debug. And finally, we need to wrap all the variables in the context and pass it to the next function after every action. What we would like to do is we would like to still detect the properties of the function based on all the calls in its body, but we want to be able to place them in different statements. We also want to be able to change the type of a variable in the middle of the function. So here we have an iterator. After pushback, it will become invalid so that it will no longer be able to be accessed. And after reassigning, it will be valid again. We also want to be able to work with costume types or costume logic. So if I have my own container or my own implementation of vector with different invalidation characteristic and different performance, then I want to also be able to validate it. It also needs to take into account control flow. So here we have a branch where in the if statement we clear the vector, and in the else statement we try to access an index. The access is valid because it cannot happen in the same control flow when we clear the vector. However, if we try to access the vector after the branch, then it will not be valid because it may have been cleared by the if branch. But there is an issue with doing all this, and this is most stuff in compile time are constant. If we declare a variable, we can't change its type in the middle of the function. We definitely can't change the type of the variable by calling a method of the vector, and for sure as not, it can't take into account the control flow or where it's placed inside of the function. I mean, doing something like this seems like it completely breaks the rules of the language. There is absolutely no way that something like this exists in today's C++. He said sarcastically, introducing the compiler loophole of stateful metaprogramming. It is the result of combining three seemingly innocent C++ features, which are: a French function exists outside the class, which is declared in, so it can belong, for example, in the global namespace. Now, when a template class is instantiated, it also instantiates all the French functions that it defines. So they will be added to the scope that they belong to. And finally, a function can be detected at compile time. Let's see how we can use all of this. So a state will use to represent a type, a changeable type at a given point in the compilation. And whenever we change the type in the middle of the compilation, the count gets incremented by 1. So you can think of it like a version number where the highest count represents the most up-to-date state. A reader will be used to detect the existence of a friend function with a given count value. So it takes the count that we try to detect and also tag, which is sort of a unique ID for this changeable type. And we can use it to have multiple changeable types. Finally, the getLastState function will first try to detect the injected friend function with the count value of 0. If it detects, then we try again with the count value of 1 and keep incrementing it until we find the first count value that doesn't exist. Then we decrement it by 1 to get the last version of the count value and call the injected friend function to get the latest state. Now, the setter takes the count value and a type, and it will inject the friend function, which we will be able to detect later. Then in the setState function, we first call the getLastState function to get the most up-to-date type. We extract the count to it and increment it by 1, so that now we have the new highest count value. And we instantiate a setter with the new count value and the new type, so that it will be detected later. Once we have a getter and a setter, we can combine them to create a metastate, which will be the changeable type. Now, it first initializes a setter with a count value of 0 and the initial type. It also exposes two aliases to get and set the current type in the metastate. And this is how we can use it. So we initialize a metastate with the type of int, then get the type from it to create a local variable of type int, after which we change it to be stood string, and then we use it to create a variable of type string. Now, the detection of the friend function happens whenever the template is instantiated, and each template specialization is instantiated once. So if we will call the function with the same template parameter, it will not instantiate it again and again, and we will not be able to get the most up-to-date type of the metastate. The way to get around it is by using anonymous lambda. So here we have a function that has a default template parameter of anonymous lambda. For each call of the function, and all of them are the same, it's just different syntax, but they all do the same, and they will all make the compiler create a new anonymous type of lambda, and therefore it will create a new template instantiation because each one is a different template parameter, and we will always be able to get the most up-to-date type. Now, in order to access and modify the metastate from within a function reliably, it must happen either inside of the template parameters declaration or inside of the function body only if it has some kind of auto return type, so like auto or decal type auto, etc. Now, my first approach to validation with metastates was to attach a metastate to pretty much everything, every function, every scope, every variable, and then in each function call validate and update all of them. This approach works for some simple validation rules, but it doesn't scale because some rules require reasoning of the complete state of the function, and this is not always available at a specific function call. It is also difficult to find and update multiple metastates at the same time, and we want to have multiple validation rules at the same time. So we are going to have like a few for performance and a few for memory safety and a few for software safety, and we want to apply all of them at the same time. So we need a different approach. Now, what does it mean for a function to be valid? We can think of a function as a set of states that can be reached whenever it runs. And so if all the states that can be reached are valid, we can say that the function is valid. Now, the state at any given point in the function can be computed from all the actions that came before it. So if we have all the actions, we can compute all the states and validate them. Let's implement it. So a counter is a compile time incrementing counter. We will use it to assign unique IDs. And we have a metastate that is initialized with the value of 0. And whenever we try to get the next value of the counter, then first we extract the value from the metastate, we increment it by 1, and we set it back again into the metastate. A value list is a list of compile time values, and it takes them all as a non-type template parameters. Then a recorder contains a metastate of a value list, and we will use the recorder to record and store all the actions inside of the function. Whenever we record a new action, we get the current list, we push back the new action, and we store the new list. The unpack actions functions convert a value list into an array of variants because it is an easier container to work with. So we first take the types of all the values in the value list, we remove all the duplicates, and we convert it into a variant. Once we have the variant type, we can use the spread operator to unpack them all into a stood array of this variant type. Now, a rule is used to validate some compile time constraints, and it has two parts. The mixin is the interface of the rule, and it is responsible to record actions into the metastate. There is also the validate function, which will take the recorded action and will return an optional error. A profile state will contain both of our metastates, so it will contain the compile time counter and also the recorders that we will use to record the actions. Finally, a profile is a composition of rules, and by itself it doesn't do much. The real work happens inside of the validator type inside of it, which will first, whenever it is instantiated, will also instantiate a profile state with both of our metastates, and we'll pass it to each one of the mixins while inheriting from all of them. So it will give access, each mixin will have access to the same profile state, And because the validator inherits from all of them, it will contain all of the interfaces. It also has a validate function that will validate each of the rules. And this is how it is implemented. So we first unpack the actions to get the stud array of variants, and then call the validate function of each rule with the actions. If an error is detected, then we return it. Otherwise, if none of the rules returned any error, then we return a null optional. The run function validates a lambda with a given profile. So first we create a validator for that profile. Then it calls the function with the validator, which will run the function, but at compile time, it will also record all of the actions into the validator. Then we can validate to try to detect an error and report it. And we have a working error detection and reporting mechanism. However, while it is the error that we want to report, this is not the place that we want to report it from. We want to report the error from the actions that caused it. So that it will point to the right location and the error can be fixed quickly. Let's implement it. So the validation error type will contain the action index, so where to report the error, and the message, which error message to report. Then inside the recorder, we pass the validation error as an on-type template parameter, and whenever a new action gets recorded, we compare the index of the new action with the index inside of the validation error. If they are equal, then we report an error from this location. Now we are able to get the error message by first instantiating a validator and then calling the function with the validator, but this time it is inside of a decal type. So the function will not run, but it will still record all of the actions. Then once we have the recorded actions, we can get the actual error and then pass it into the function with a new validator. Whenever the actions get recorded into the new validator and we reach the action with the error index, then the error will be reported from this location. Let's implement some validation rules. We will record every access to a variable with a borrow action. The ID specifies which variable we are accessing, and the borrow type specifies the access type. I'm going to use Rust terminology here, so excuse me, but a reference is a read-only access reference, and mute is a read-write reference, or mutable reference. By tracking when an object gets modified, we can prevent the invalidation problem. The borrowable class provides access to a variable through member functions, and it also records this access. So when we try to get a const ref, we will report a ref action, and when we try to get a regular reference, we will report a mute reference action. Then inside of the borrow rule, in the mixin, we expose an interface to create a new borrowable type that will first increment the counter to assign a new ID for each variable, and also pass this ID along with the recorded so that it will be able to record the actions into it. The constraint that we want to validate is that at any point in the function, a single variable can either have multiple read-only references or a single mutable reference. We can do it with the borrow state, which initializes both counts to 0. Then whenever we receive a new action, we increment the appropriate counter and validate this constraint. The borrow rule validation function contains a vector of borrow states, and it iterates over them. So we have a vector where each element is the borrow state for a specific variable. First, when we encounter an action, we resize the vector to make sure that each variable has its own borrow state. And then we call the borrow state and pass it the borrow action type. If the state becomes invalid, then we report a validation error with this specific index. And this is how it looks like. So we can create a profile with the borrow rule and then use it to validate a lambda. We first create a borrowable variable. When we call the ref, it will increment the ref count. When we call mute, it will increment the mute count. And this breaks the constraint of the borrow rule, and it will cause a static assert with an error from this function call. We also want to take into account the control flow. And here we have an enum class that represents all the control flow actions. And one way to do it is to manually record each control flow information. So we can record whenever we start an if and whenever we end the scope. But this is not ergonomic, so let's do something better. When a macro converts text to string, it removes all the comments and collapses all the white spaces. So below you can see a very badly formatted if branch with a lot of comments. After the conversion to string, it becomes a lot clearer, and you can see it is the same as the string literal in the string view here. So a lot more clear, and we can parse this clear string into a control flow action. So here we have a few branches to compare which action it is. This is far from being a fully functional compile time C++ parser for the entire syntax, but it does the job for this case and for our purpose. Then we can create the control flow parse rule, and the mixin will expose a parse alias that takes the compile time fixed string of the code. It parses it into the control flow action and adds it into the recorder. Then we can have a macro that uses the same text twice. First, it converts it into a string literal and will pass it on to be parsed and recorded. Then we can also use the text as is. Now here we have, so that it will be compiled. Here we have a few lines of code. Each of them have some control flow information. And if we want to record it also that we will be able to validate it later, then we can wrap each line with a macro. Now it does add some syntax overhead. Once we have the control flow information, we can extend the borrow rule to handle multiple scopes. So here we have vector of vectors of borrow states. And this is our scope stack. So whenever we enter a scope, we copy the current state of the current scope and push it onto the stack. So we create a copy. Then all the actions happens on the copy, and whenever we exit the scope, we pop back the copy, and we are reverting to the state that we were before we entered the scope. Let's create another rule, and this one will be for pointer validation. So in C++, we can have a pointer in an outer scope into a variable inside of an inner scope. When the scope ends, then the variable gets out of scope, and the pointer is dangling. Let's enforce that it doesn't happen with a rule. First, we need to record actions, and we will record whenever we initialize a pointer and whenever we do an assignment. Then our pointer type will contain a regular C++ pointer, and it will also has an assign method that will record the assignment command with the identifiers of both pointers. Next, inside of the validation, whenever we reach a control flow, we keep track of the current depth of the scope. So whenever we start a scope, we increment the depth by 1. Whenever we exit a scope, we decrement it. Then whenever we initialize a pointer, we store the depth of that current pointer. And whenever we have an assignment between two pointers, then we validate that we are not having an outer pointer pointing into one in an inner scope, so that we can never have a pointer in an outer scope pointing to an inner variable. All right, so it's time for demo. So let me. Okay, so here we have a profile, which is the safe profile, and it contains all the rules. It contains the control flow parser, the pointer rule, and the borrow rule. And we create, Okay, and it creates a pointer in the outer scope into the borrowable type, and also another pointer in an inner scope. Now, if we try to assign the pointer in the outer scope to the inner one, then we will get a compilation error. 1 second. That says that the lifetime is not long enough. And if we can see that it is reported from this location. Also, if we try to clear one of the vectors, then we need to create a mutable access to it. And this will also cause a validation error, because we're taking a mutable reference into it when we create the pointers. So we will have one mutable and one immutable, and this will trigger the borrow rule validation. Outside of the scope, then we can create a mutable reference because we have the control flow information, and we know that by this time we no longer have any more references. And once again, if we try to create two mutable references, then it will fail. Now it fails the same on all the three major compilers, and if I recommend it back again, then it will compile on all the three major ones. Okay. Sometimes we want to be able to handle multiple control flows. And we can find them with this. The control flow path struct represents a single control flow through the function. So here we have the action, which is the next action to consider, and the vector of all the actions in the current path. In order to find the path, then whenever we process a single path, if we reach a branch action, then we copy the current path, we make the copy skip the branch, and we store it to be processed later, while the current path enters into the branch. So this is a depth-first search inside of a graph. We can use it to validate cleanup. Now you ask, why would you want to validate cleanup? We have RAII. You call the cleanup function at the destructor, and the compiler makes sure it does it for you. However, in this case, it is not possible because the cleanup function is a sink, and a destructor cannot be a coroutine. So we have to call it manually, which is error-prone. So if we can, once we detect the control flow path, then we have one that goes through the if branch and another that skips it. And for each control flow path, we can validate that we clean up the resource exactly once. It is also possible to validate and detect performance issue. So a general purpose allocator is slow. So in graphics programming, we often have a frame allocator, which is fast and can allocate variables that are only used. We can only use it for variables that we know that are used only within the current frame, because in the end of the frame, it will free everything. Now, because we have all the actions recorded, then we can find how the variable is being used in the function and see that it matches the correct allocator. In this case, from the action, we can see that it is only used within the current frame, but it is using the general purpose allocator. So we can report an error that says that we are missing some optimization here because we are not using the most optimal allocator. If you remember, we get the actions to the functions before we actually run the function. So because we use the decal type trick when we invoke the validator, and then we have all the actions. So then we can pass the recorded actions inside of a lambda back into the functions that recorded them. Then we can furthermore pass them into the constructor of the buffer and use design by introspection. Now, when you think of design by introspection, you usually think about using a pointer. So if you have a function that needs to do some algorithm with pointers, we first ask the pointer, what type are you? Are you a random access pointer, or are you a forward-only pointer? And then based off it, choose the most optimal algorithm. We can do the same because we have the recorded actions inside of the function. So we can ask the actions, how is this variable going to be used in the rest of the function? Once we have this usage, we can choose the most optimal allocator for it. The pros of this approach is that first we are able to validate compile time constraints at compile time. There is a separation between the recordings of the action and the validation of the action, so that we can have multiple types record the same action and they will be validated the same. Or we can have multiple validation constraints reusing the same actions. We can also choose validation rules and combine them into profiles and choose which profile we want to apply to each specific function. We can introspect the function actions at compile time and use it to optimize the runtime performance of it. And finally, whenever we get an error, then we can report it with a costume error message from the place that caused it. Now, it also has some downsides. First, it can only validate based on the recorded actions. So if something is not recorded, then we will not be able to validate. It also requires proxy types to record some of the operations. For example, by default, the regular C++ pointer is not recording actions, so we need to create our own wrapper around it to record these actions. It uses macros to record the control flow. And finally, it uses the compiler loophole for stateful metaprogramming. And once again, this is a loophole. This was not something that was intended by the language, and this is not something that is defined by the standard. If used incorrectly, it can cause a lot of not so nice compilation errors and even ODR violations. So be careful if and when you choose to use it. With the cpplusplus reflection proposal, we can access the meta information, and we can use it to create more generic actions that we record. So instead of having specific assignment action or ref action or borrow action, we can have a generic action that takes the meta information about the function and the meta information about all the arguments. Then we will store them, and the rules can later query this meta information to validate the constraints that they need to. Here on the right, you can see a list of some of the meta functions that are available with the cpplusplus reflection, and this is a small part of it. The list is a lot longer. And so with all this information, we can enforce more complex constraints. As mentioned before, we also need to create proxy types. And with the C++ reflection, we have the define class function, which we can use to create new types. So we can get all the members of the types that we want to create proxy of, create the wrappers around it, and then use it to define a class. And finally, cpplusplus reflection has the this is complete type function, which detects whether a template was instantiated or not. And we can use it to implement compile-time stateful metaprogramming. Here is an example of compile-time stateful metaprogramming counter. And as you can see, the code is a lot more clear than the friend injection version of it. And also, I didn't write this code. I took it from the cpplusplus reflection. So this time, the stateful metaprogramming will be defined by the standard and will not be a loophole. Now, Circle is a C++ compiler by Sean Baxter, and it has many languages extensions. One of them is the features, the safety feature. When it's enabled, we can mark functions as safe. Once a function is marked as safe, it prohibits some operations from being used inside of it. For example, we cannot use regular references, we cannot use pointers, and we cannot call any function which is not marked as safe. If we still want to do it, we have to put this code inside of an unsafe block. Now, it also had some syntax extensions to the language. One of them is the the int caret here is a mutable borrow reference. So the compiler keeps track of how many references are alive at any certain point for a given variable, similar to how we saw before. And it also contains lifetime annotations. So the /a is a lifetime annotations, and we can use it to tell the compiler the relationships between references. In this example, we use it to explain to the compiler the relationship between the function arguments and the returned reference. In this case, for the getMax function, the relationship is that the returned reference must be contained inside of the lifetime of both arguments. Here we have an example. So we start by initializing a variable called x, and this starts its lifetime. Then we enter into a scope and initialize variable y. This starts the lifetime of y. And then we call getMax of the references of x and y and store it inside of a reference. Now, this reference is only valid to use inside the lifetime of both variables. So when we exit the scope, y gets destroyed and its lifetime is ended. If we try to use the reference outside of this scope, we will get an error because it is not contained within both lifetimes. Then we create a variable x and call getMax of the references of x and z. So now a reference can only be valid to be used inside of the lifetimes of x and z. The next line is another language extension, which call rel of x, and this is destructive move. So at this point, X gets destroyed, and it also ends its lifetime, so it is no longer valid to be used. And if we try to use the reference after this point, we will also get an error. There is a lot of progress in the recent years about C++ safety, and there are many different ideas for improvement. There is the profiles proposal by Bjarne Strustrup, and his talk in last year's CppCon was one of the reasons that I decided to look deeper into this topic. There is also the circle lifetime extension, which we just saw, and there are many other proposals that tries to improve the safety of C++ on various scales. And there are also other projects not related to proposals that attempt to do it. Overall, I think we are still in an early phase, and that is currently focused on the exploration. And it will take time until we will find out which approach the language and the industry will take. Now, talking about C++ code is not something new, but in recent years there was a change in how we think about it. We sort of borrowed Rust perspective of safe and unsafe code. And while this is a good starting point to think about memory safety, it comes with limitation. And this, we can either have all of the constraints of the borrow checker or none of this. And this is not so flexible. So for example, here we have the classic vector and reference. And if we call pop back and then in place back, then the reference will always be inside of the valid range of the vector, and it is safe to be used. However, if we replace the order of pushback and in place back, then the vector can potentially grow and the vector will become invalid. Why am I telling you all of this? Because this code, even though it is valid as it is right now, it will not compile in Rust because it does not satisfy the constraints of the borrow checker. It will compile in unsafe Rust by using pointers, but if we will replace the order of the pop back and in place back, we will not get any compilation error, even though we have invalidation issue. So I argue that there is no such thing as unsafe code, only code that we can't explain the constraints that make it safe. In the previous slide, I explained the constraint to you in English, and you were able to validate it. And if we are able to explain the constraints in C++ and make the compiler understand them, then we can have code that is both flexible and safe at the same time. And we saw that there are plenty of validation constraints that we can already express today. And with future improvements to the language like reflection and other C++ 26 features, it will only become better. And we should be talking more about valid code, because memory safety is only part of security, which is a small part of validation. There are many other validation requirements that an application have. Now, don't get me wrong, memory safety is important, but I'm worried that if we focus on it too much, we may miss the bigger picture. Finally, Mitzi is a header-only library for creating and validating costume constraints at compile time. It uses C++26, and I'm planning to use it uses C++23, and I'm planning to use C++26 reflection and other features once they will become available. It is in early development, so it is not ready for production yet, but it is currently available on both GitHub and Compile Explorer. So if you want to create your own validation rules, play with stateful metaprogramming, or see the full implementation, then you can do it today. And finally, this is Mitzi. She's my cat, and she has passed away earlier this year after giving me the most wonderful 18 years with her, and this is all dedicated to her. Thank you.